Now we're going to look at part B of the problem, where we have the charge distributed uniformly throughout the volume of the sphere. Okay, so in that case, we have a uniform volume charge density. So this is part B of this problem. Uniform volume charge density that I'm going to call rho. And this density is basically the electron charge minus E divided by the volume of the sphere 4/3 pi capital R cube. So this will be equal to minus 3E divided by 4 pi capital R cube. Okay, now the next task is to calculate the charge on a volume element. So then the charge on a volume element dV is dq, infinitesimal charge, that is equal to rho times dV, the uniform volume charge density times the volume. And for the charge density, we have found minus 3E divided by 4 pi capital R cube. Now we have to recall the volume element of a sphere. So we have seen at the beginning that the volume element will have r squared sine theta d theta d phi. So sine theta r squared dr d theta d phi, and r will be varied between 0 to capital R, theta between 0 and pi, phi between 0 to 2 pi to cover the full sphere. Okay, so it's going to be r squared sine theta d theta d phi dr. Okay, so we know the charge in a volume element dV. Now the tangential speed we have for this volume element with charge dq will be equal to 2 pi r sine theta divided by the period. So this volume element is rotating. So if you take this volume element here, it's going to be rotating in the circle, and we will have 2 pi r sine theta, well, where r is less than capital R, divided by t. Okay, so r is between 0 and capital R, and with that we can write the current, the contribution to the current will be dI, which is the infinitesimal charge dq rotating in one period, capital T. So capital T was our period of revolution. So with that, my dI will become minus 3E over 4 pi capital R cube so I have r squared sine theta d theta d phi dr, and for the period I substitute 2 pi r sine theta over v. So because it's 1 over the period, it is v over the tangential speed v over 2 pi r sine theta. Now you can see that this r sine theta will get rid of this r sine theta here. So you'll be left with a single r on top. And then the contribution to the current di will be minus 3e vr d theta d phi dr divided by 8 pi square capital R cube. Okay, so now we know the current. Now, what is the area enclosed by this current loop? The perpendicular area that is enclosed by this current loop di is basically pi times r sine theta squared. So this current will be flowing in this circle. Let's say this is my r less than capital R. It's on this circle. So basically we have a current loop here, and r sine theta will be the radius of the circle. So it will be pi r sine theta parentheses squared. Now we are ready to calculate the contribution to the magnetic moment, so that using the SI definition of magnetic moment, the infinitesimal moment d mu will be the perpendicular area multiplied by the current di. So this will be minus 3e vr divided by 8 pi square capital R cube d theta d phi dr multiplied with the area pi r square sine square theta. And as you can see, one of the pi's will disappear here, and we will find the contribution to the magnetic moment d mu to be minus 3e v r cube sine square theta d theta d phi dr divided by 8 pi capital R cube. So this is the magnetic moment due to this small current loop. And we have this relationship between v and omega. V is equal to omega times the radius of the loop, which is r sine theta. And we know that omega was 5 h bar over 4 mass of the electron capital R squared. So this will be multiplied with r sine theta to find the tangential speed. So we can substitute this result for v into the magnetic moment equation. So d mu will become then minus 3e r cube divided by 8 pi capital R cube sine square theta d theta d phi dr multiplied by v, which is 5 h bar r sine theta divided by 4 mass of the electron capital R squared. So this gives us a d mu minus, now 3 times 5 will give us a 15. So first we have a 15, then we have the electron charge E, then we have this h bar h bar, and r cubed multiplied with r will give us r to the fourth power. Sine square multiplied with sine gives us sine cubed theta, d theta d phi dr, divided by 8 times 3, 32, mass of the electron, pi capital R to the fifth power. So this is our infinitesimal magnetic moment. Now we can calculate the full magnetic moment by adding up the contributions from all such volume elements. So all the current loops will add up to a total magnetic moment mu, and for the integral between 0 and 2 pi d phi, this is just going to become 2 pi. So mu is going to give me integral from 0 to pi, that's the theta integral, integral from 0 to capital R, R integral, minus 15 e h bar r to the fourth power, the 2 pi comes from the phi integral, divided by 32 mass of the electron pi capital R to the fifth power, sine cube theta d theta dr. Actually, I'm performing the r integral first, so it's dr d theta. So I have as simplification here, the 2 pi will get rid of this pi, and this 32 will become 16. So now my integral will become integral from 0 to pi, integral from 0 to capital R, minus 15 e h bar r to the fourth power dr divided by 16 mass of the electron capital R to the fifth power, and then I have sine cube theta d theta. If I perform the r integral, I will be left with this theta integral, 0 to pi, minus 15 e h bar. Now r integral, r to 4 dr gives me r to 5 over 5. Between 0 and capital R, that will be just r to 5 over 5. So 16 mass of the electron, r to 5, and then I have r to 5 over 5, and I'm left with sine cube theta d theta integral to perform. And now you can see this r to 5 terms cancel, and this 5 will make this 15 3. And I'm going to isolate a Bohr magneton in this result. So mu is equal to, so I want to write minus EH bar over 2ME at the front. So this is going to give me a Bohr magneton minus EH bar over 2 mass of the electron multiplied with, and now I have, since I have the 2 mass of the electron isolated, 3 over 8 left. So this will be 3 over 8. And then I have the integral from 0 to pi sine cube theta d theta. Once again, we have performed this integral several times already. The answer was 4 over 3. So we recall this result. This is a recall. So we can substitute that result here. Minus 3 over 8, a Bohr magneton. A Bohr magneton is EH bar over to mass of the electron, times 4 over 3. Now you can see these 3's will cancel and 4 will make this 8, 2. And we see the total magnetic moment minus 1 over 2 Bohr magneton. So when we assume that the charge is distributed uniformly throughout the volume, the magnetic moment of the electron spin turns out to be minus 1 over 2 Bohr magneton in this model. So in summary, we're continuing our calculation with the uniform volume charge density. The last time we did uniform surface density, the answer was minus 5 over 6 Bohr magneton. With the uniform volume charge density minus E divided by the volume of the sphere, 4/3 pi r cube. First, we calculated the charge on a volume element, rho dV, where we have substituted for dV r squared sine theta d theta d phi dr. The tangential speed for this volume element at a radial distance r from the origin is 2 pi r sine theta divided by the period, and the current due to this charge flowing in one period, rotating about the z-axis in one period, is dq over t. For t, we substitute 2 pi r sine theta over v. So 2 pi r sine theta over v goes upstairs, v over 2 pi r sine theta. So we calculate di. And the current enclosed by this element is basically this area. So this is at a radial distance r, angle theta from the center, and so that area is pi r sine theta parentheses squared. So we have seen that when we introduce this current multiplied by the area to calculate d mu, we obtain this result. Then we have the relationship between v and omega. V is equal to omega times the radius of this current loop, r sine theta. And omega we have obtained in the first video, 5h bar over 4 mer squared. So we substitute that result here. Once we obtain d mu, we integrate over the full volume of the sphere. Integral 0 to 2 pi d phi gives us 2 pi. Integral 0 to pi sine cube theta d theta gives us 4 over 3. And 0 to capital R gives us capital R to 5 over 5. So by multiplying all of these factors and noting that a Bohr magneton is EH bar over 2 ME, the final result we obtain is minus 1/2 Bohr magnetons.